Well, good morning, Green Wave. This is Mr. Brisky, and today what I want to do is to talk about double replacement reactions. This is typically a lab that I would do in class, but obviously, circumstances being what they are, this is what we're going to do. I have an online lab. Unfortunately, the online lab is not compatible with the iPad. Resources that use the iPad for chemistry just simply don't exist. There are a couple PHET simulations, but that's about it. But that's okay. We'll make the best of this. So I have a simulated or virtual pipette with silver nitrate. Okay, and I'm going to react it with a couple different compounds. Potassium chloride, if you'll follow my cursor. Sodium carbonate. Potassium nitrate. Sodium phosphate. Some of this naming might be familiar to you from last semester because we did cover it in the ionic compound unit. But if you don't remember the names, excuse me, that's okay. It's okay if you don't remember the names. So let's take a look at silver nitrate, at least, so the one on top. Let's take a look at what it looks like in water. Okay? As you can see, the water molecules surround the ions because silver nitrate dissociates. If we go back over to look at this slide, okay, this is going back to last semester. Remember, water is polar. Water has a positive end and a negative end. Okay, the negative ions attract the positive end of the water molecule, and the positive ions attract the negative end of the water molecule. Okay, it's called an electrostatic interaction. Now let's take a look at the simulation. Okay, let's take this pipette of silver nitrate and we're going to put a drop in potassium chloride. And as you can observe, the potassium chloride turns white. So let's take a look. So potassium chloride also dissociates in water to form these ions. Okay? Now when we introduce silver nitrate ions, what we observe is that the silver and the chloride come together to make a solid compound. So the silver, the Ag+, and the chloride, the Cl- ions, come together to form solid silver chloride. That's why the solution turns white. Okay, if we were to write this out as a complete ionic equation, this is an equation that shows all the different ions in solution. So this complete ionic equation shows me all of the different ions in the solution, okay? Now, if we notice that these potassium and nitrate ions don't change as a course of the reaction, they're called spectator ions. Okay, so if we get rid of spectator ions, we can write a reaction called the net ionic equation. All right, the net ionic equation is an equation that tells me which ions change over the course of the reaction. And then finally, we have the molecular equation that gives me an overall summary of everything that's going on. Now, I personally would not write a molecular equation showing ions like the example here in this module, all right? But this is one way you could write a molecular equation, but again, I don't think it's so common. It's more common to just write KNO3 aqueous, just like the AgNO3 aqueous is here in the product, in the reactants. So let's take now the AgNO3 and react it with Na2CO3. So we're going to take silver nitrate and react it with potassium carbonate. That forms a product. The sodium carbonate dissociates, and then the silver ions come in and link up with the carbonate ions. So silver carbonate, or Ag2CO3, is my product. This is the complete ionic equation for that process. And here's my net ionic equation for that process. The net ionic equation, as you remember, involves getting rid of the spectator ions. And here's my molecular equation. And for molecular equations, I would want you to write NaNO3 aqueous, not Na plus and NO3 minus. So let's go back to the lab now, and let's take silver nitrate and react it with potassium nitrate. So, as you see, no reaction happens, nothing happens. So let's figure out why. So potassium nitrate dissociates in water, just like this. All right. Now, when we introduce silver nitrate ions, there's nothing to link together. There's no ions that form a product that's solid. Okay? So because of that, there's no reaction. Now let's take the silver nitrate and add it to sodium phosphate. Here we observe a product. So sodium phosphate also dissociates in water. So when we add the silver nitrate ions, what we observe is that the silver and phosphate ions come together to make a solid product. So if we were to write the complete ionic equation for that process, it would look like this. And if we get rid of spectator ions, it would look like this. And so the molecular equation would look like this. And once more, I would combine this together as one term for a molecular equation. So in this lab, you have seen different examples of double replacement reactions. The idea of a double replacement reaction is that both metals trade places with both nonmetals. In the single replacement reactions you saw before, only the two metals would trade places. Okay? The way you can tell if a double replacement reaction works is if a solid product forms. If a solid product does not form, then the double replacement reaction does not work. And so the way you can predict if a solid will form is using something called solubility rules. And tomorrow I will be introducing how to use solubility rules in order to predict the products of a double replacement reaction. But for now, this concludes my lesson on this simulation. I hope you guys get something out of this. I hope you understand how ions work, how water causes ionic compounds to dissociate, and how double replacement reactions come about as a result of insoluble or materials that do not dissolve in solution.